Alright, so today I'm going to be explaining this important paper with the title A Simple and Scalable Representation for Graph Generation. This ICLR paper in 2024. There has been a surge of interest in employing neural networks for graph generation, a fundamental statistical learning problem with critical applications like molecule design and community analysis. However, most approaches encounter significant limitations when generating large-scale graphs. This is due to their requirement to output the full adjacency matrices, whose size grows quadratically with the number of nodes. In response to this challenge, we introduced a new simple and scalable graph representation named gap-to-encoded edge list that has a small representation size that aligns with the number of edges. So GEL significantly reduces the vocabulary size by incorporating the gap encoding and bandwidth restriction schemes. GEL can be autoregressively generated with the incorporation of node positional encoding, and we further extend it to deal with attributed graphs by designing a new grammar. This is an overview and advantage of gap-encoded edge list. So we propose to autoregressively generate it, GEL, by incorporating node positional encoding and combining it with an LSTM of order of M complexity. So we define the edge list as a sequence of pairs of integers. And these are S and T. It means M source and the target node indices that satisfies this ordering like this, because pi is an ordering as is an invertible mapping. From each node it says which order, from vertex to its rank for a particular order of nodes. So there is an ordering approach. And we define our GEL as a sequence of gap encoding pairs. So A and B are the inter and intra-edge gap encoding, respectively. To be specific, the inter-edge gap encoding indicates the difference between consecutive source indices. Here, in training a generative model for edge list and GEL, the vocabulary size determines the complexity of the model. We show that the vocabulary size is B squared for graph bandwidth B, which is smaller than the vocabulary size N squared of the original edge list representation. So molecules usually have a low bandwidth, and the vocabulary size of our GEL representation is bounded by this. We can obtain the following upper bound for the inter-edge encoding. So we first describe our method for autoregressive generation. We maximize the following lower bound for the autoregressive graph generative models, and C is just a constant. So Q is a variational posterior of the ordering given the graph G. Our choice of choosing C and M ordering for each graph corresponds to a choice of the variational distribution. Fixing a particular ordering for each graph yields the maximum log likelihood objective. So the colored parts of attributed GEL denote the node features and edge features. The shaded parts denote the self-loops added to the original GEL, where self-loops are added to the nodes that are not connected to the nodes with larger node indices. So we directly supplement the token embedding with the node positional encoding of source node index. Phi is the final embedding. Phi of tuple is the token embedding. This is the positional encoding. And for generation of attributed graphs, we also generate node edge according to these rules. So before describing edge tuples starting with a new source node, add the paired node type. After adding an edge tuple, add the paired edge type. To enforce the attribute grammar, we introduced an algorithm to filter out invalid choices of tokens. The first token is always the node type token. The node type tokens are always followed by edge tuple tokens. The edge tuple tokens are always followed by edge tuple, but by edge type tokens. The edge type tokens are always followed by node type tokens or edge tuple tokens. And they compared different kinds of graphs like planar graph, lobster, enzyme dataset, and they compared graph variational autoencoder and other methods like graph gen to GEL. So these are different methods for large graphs, that when the number of vertices is this big, then they also compared it in a different table. And this is the graphs that are generated by their method here in comparison to the popular digress method. For enzyme, the generated graphs of GEL is here. And QM9 dataset as well as zinc dataset are very important for graph generation. Zinc is here for graph generation